Philosophically, yes, we really care. Chemically, do we care chemically what the mechanism is? Is this something that we need to be worried about? Right. Well, let's take a look at our 3 reactions that are all ultimately related to each other, 4 reactions. Okay. What happens when I compare this one to this one? Do I get a different result? Yeah. So do I care what the mechanism is? Well, yeah. Okay, but then you could make the argument, well, that's really just the reaction, be it substitution or elimination. I don't really care what the mechanism is, because when I compare the product of a substitution SN1 to the product of an SN2, I get the exact same product. So, well then, oh Mike, I still don't care. Well, now I don't care for real. Okay? What is special about our starting material and our products? I heard an OH, which I don't understand, so I probably misheard that. What'd you say, Joey? Okay, don't understand the question. If we look at just the starting material, there is something characteristically special or interesting about this molecule. Shape is not it. Not the energy. Sort of the leaving group. Where the leaving group is placed, that atom has 4 different things attached to it, which means that atom is chiral, which means if I become a jerk and add some chirality information into this and call that a wedge, how does that change my products? Well, it turns out the products in my SN1 look kind of similar. Except I get 2 products. In the SN2, I only get 1. Right? So do I care now what mechanism my reaction runs under? Yeah, there's a pretty significant difference between those products. And depending on what I'm trying to make, that could be a bit of an issue. The SN1 already screams an issue because if I'm trying to make one thing, how many do I make with the SN1? 2. So the highest percent yield I could ever get? 50%. Synthetically, that's pretty awful. Okay? So that's not a good sign. What happens when we move to the elimination? That one becomes significantly harder to see, and the real difference there is going to pop in with very specific molecules. Right? What is special about the product in both of those eliminations? We have the potential for cis and trans. Okay? In the case of the E1, which one's the E1, the top or the bottom? How do you know the bottom one is? I'll kind of accept 2 steps. We've got to be careful with that, though, because we could throw in an acid-base step, and that's not part of the mechanism. Carbocation. Right? It's the carbocation intermediate. That's your tip-off that you're doing a 1-type mechanism. Okay? The product of your 1-type mechanisms for your elimination are almost always trans. Why would you never form cis? So we're saying it's E1, and you're saying I can't form cis because it's E1. Oh, yes, it is E1. Yes. So why can't we form cis? What's that? A bendy straw has more energy. You're getting at a right idea, though your analogy makes no sense, at least to me, about the bendy straws. What's the difference between cis and trans? Same side. What's on the same side? My large groups. If my large groups are on the same side, what happens? It is higher in energy because they bump against each other. That makes the cis higher in energy. In an elimination or in all reactions, what should I be trying to make? the lowest energy. Okay? So trans will dominate. Okay? I can get cis. Okay? It's usually kind of a mixture. It just kind of depends on the energy of your intermediates, okay? Or technically of your transition states. But for the most part, we get trans. What happens when we move to the E2? E2, it's all happening at the same instant. The hydrogen is getting removed at the exact same instant that our leaving group is leaving. How many hydrogens are possible? Well, in this structure, there's 2 that I could remove. I could have removed the wedge hydrogen, which I've got now in purple, or the red hydrogen, because it's all happening at the exact same time. Just like the SN2, the electrons of our nucleophile must come in from the back side. Guess what's happening in the E2? Kind of the same thing. The electrons used to make the pi bond must be coming in from the back side of the leaving group bond leaving. Which hydrogen is on the back side of that leaving group? The dashed hydrogen. So I can only eliminate that one. With this structure, does it matter? Well, with the sigma bond in between, I can freely rotate. Because I now have the choice of which of those hydrogens to eliminate, I'll eliminate the one that puts my structure at the lowest energy possible situation. But what happens if I remove one of those hydrogens and replace it with bromine's a bad choice. Another carbon group. Can that hydrogen be eliminated in this configuration? No. So what has to happen? Hint, green. We have to do a rotation to get the purple hydrogen to be anti to the leaving group. Is that rotation going to change the respective alignment of those now purple groups? Yes. Which means the product I get will be singular. It'll be cis or trans, but cis is now absolutely possible. Okay? So the E2 elimination becomes tricky. I do end up with only one possible product. With the E1, I have the option for 2, though it typically heavily favors the trans. Okay? And it all has to do with how the mechanism worked. So is it important to know the mechanism? Yeah. That dictates how many products I get and what products I should expect in different yields. So it becomes critical for me to be able to look at an individual reaction and say, that is an SN2 mechanism. That is an SN1. That is an E1. That is an E2. Is that something that is easy to do? No. Okay. That becomes a challenge, and that's really why Chapter 9 is there. Okay. So this is kind of a preface for Chapter 9. What we'll spend most of Chapter 8 doing is saying, it is an E2. What's the product? It is an E1. What's the product? So you're making the initial assumption that it is running that mechanism. Regardless of you look at it and go, oh, it shouldn't do that. It should do this. That doesn't matter. You're being told that that's what it does. What is the product going to be? Okay, that's Chapter 8. So it's looking at the results, kind of the repercussions of each of these mechanisms. Chapter 9 then goes through and says, well, if I just give you the reactants, how do you know what your product's supposed to be? You need to be able to evaluate those pieces. Those of you in lab have a jump start here. What are those pieces for, say, the substitution reaction? There's 4 of them, as a hint. Solvent, probably the least important of them. The substrate, really, really important. Nucleophile, really, really, really important. And leaving group, not so important because every single one of those requires a leaving group. Okay? So, what you should be, your textbook, I think, hopefully I got this right. Your textbook has this slide popping up, or this image table popping up in Chapter 9. I would argue there's a bunch of stuff on there that doesn't make any sense. For instance, strength. Strength of what? Wow, that's a good question. They're referencing the strength of the nucleophile. Okay? Concentration. Concentration of what? Okay? Both of those terms are really weird and bizarre. Notice leaving group. What did I say was important about the leaving group? They all have it. And look at what they've got. All checked. That's kind of a dumb thing to evaluate if every single one of them needs a leaving group. Okay? And then solvent becomes important. What you would then do is total up within your column and say, well, which of those has the most options? That's likely what's happening. So if we take a look at the reaction shown, leaving group, they all have solvent. What's the solvent in that reaction? Okay. Your solvent is typically written underneath the arrow. Sometimes it is, sometimes not. DMSO. What does DMSO look like? Guess what? You're responsible for it. You need to know what that looks like, so that when you see the word DMSO, you know that what we're referencing is, as Tristan has just suggested, dimethyl sulfoxide. Dimethyl sulf oxide. Okay. Oh, that helped, Mike. Thanks. That is an aprotic solvent. It is also polar. So those acronyms, or not acronyms, the names that we assigned to our solvents way back in Unit 1, protic, polar, aprotic, and nonpolar, you need to be able to use those solvents and recall them based off of different structures. And then you can interpret. Notice for this case that they're saying that that favors the SN2. How and why? That's a lot of what Chapter 9 is about. What I would argue is you should change it to this. That's why it's bigger, because it's cooler and better. Strong nucleophile. Notice we have NAs next to E1 and E2. Nucleophiles don't exist in elimination reactions. Okay? What's the next thing? Strong base. NAs for substitution, because I don't want a base in a substitution reaction. I want a nucleophile. Okay? After that, leaving group, which I put in insanely tiny font because they all have a leaving group. Substrate. Okay? How does the substrate affect? How does the solvent affect? Is there heat? Okay? So some small kind of adjustments have been added in to hopefully help. You should use these and rank them. You'll go through in total and you get the same results on deciding which mechanism runs. What if you total up and you get the exact same result for two different mechanisms?
Combination.
You get both. Both are now possible products, okay, which can and will happen. Yes?
So when you say heat, do you mean into or out of?
Heat into. Always a reactant. We don't have the product to be able to decide. Okay, so it's always an into. Kind of make sense? So as you're thinking of, you guys look awfully like depressed.
A little bit.
Why are you depressed? I just said that's your answers. Yeah. Test is kind of scary. What does this look an awful lot like? 152, because it is 152. This is straight out of my 152 lectures that I used to give. Wow. She didn't call me names, yeah. Okay. I'm only putting this there because I want you to be reminded of it. I'm not expecting you to do anything really with this content. Okay? Your rate law is rate times your rate constant times the concentration. Concentration has what units, Tristan?
The rate, constant rate. We're talking about solvent.
Concentrations has what unit?
Meters.
Those brackets, meters, you're horrible, would be molar or capital M. And since nobody had, well, a few of you had me for general chemistry. What does capital M immediately need to get converted into?
Moles over liter.
Moles over liter. Moles of what? whatever's in the bracket. Since we started talking at A, we'll say moles of A over liters of Tristan. Solvent. Right? This is a really important section to reference because you can get asked questions about what do different changes in the concentrations of species do to the rate. Well, if I double the concentration of A, what happens to the rate? It doubles based off of the rate law. So I have to be able to match the rate law to my individual reactions. Right? What happens if I change the solvent? Well, solvent isn't A or B. So how do I get a solvent effect? It shows up, Tristan, in the denominator of our concentrations. Meaning if we increase the solvent, what happens to the rate? It decreases because now the concentration of all of your reagents has decreased. Right? It is a very sneaky and backhanded way to get you to evaluate your 152 content in organic chemistry. Not a big fan of 152 content, so it only shows up like once. Yes?
Does it decrease exponentially depending on the number of reactants?
Yes. Your effect will scale because that increase in the solvent decreases the concentration of A and decreases the concentration of B. Both A and B decrease, which means we're getting kind of a doubling effect. Right? And I don't know math well enough to say if that's exponential or not. So it gets bigger. I'll go with the whatever part. So yes, subscripts must be, or superscripts must be proven experimentally. Okay? That's what you had to do in 152, which in theory, well, maybe not quite yet. Those superscripts are known as the order. Okay? The order is our interpretation. What do they mean? Okay? The superscripts as the number are a math. Okay? This is how we would calculate it. This is how it experimentally translates out with numbers. Okay? What we're concerned about is what does that mean? So what does it mean? If your order is 0, what does that mean about the importance of that reagent? It's not. Because anything to the 0 power is 1. It disappears from the rate. We don't have to worry about it. If it's first order, it's now involved in the reaction. If it's second order, it's really, really involved in the reaction. If it's third order, then that whole reaction is based solely on that reagent. Why only on that reagent? What we're effectively saying with our rate law is if I have a third order reagent, I need 3 molecules to come together for that reaction to occur. What are the odds I can get 3 people all together to form a cohesive, responsible relationship?
It's possible.
There's a little bit of laughter there. I said relationship.
But in
And that doesn't work very well, which is why those systems don't happen very frequently. Why do we stop at 3? Well, if 3 is really hard to do, what's going to happen at 4? Virtually impossible. Okay? So there's kind of a scaling effect. We can really only deal with orders in the 1 and 2 range. As far as organic chemistry is concerned, we only deal with orders in the 1 and 2 range. We won't see numbers outside of that. Okay? This can get referred to as the molecularity because nobody liked my little version of names as bystander involved and super involved. So we came up with other names. 0 order, non-existent. Has nothing to do with the reaction. So we don't even talk about it. First order becomes unimolecular. Uni for 1 and molecular. Second order, bimolecular because there's 2 molecules. Third order, termolecular. Okay? It's just trimolecular, that's fine. Okay? Then you went through and probably looked at reactions, and if we looked at the orders of, oh, stupid slide, I thought I fixed all this. Take a look, we've got reaction arrows in here. It's not that embarrassing. Take a look at your rates for the first one. Right? What are the orders? first order for both, right? What are the coefficients? 1 and 1. Yeah, that kind of makes sense. How about the second one?
2 and 1.
Ooh, it's 2 and 1, but the coefficients from our reagents? 2 and 2. The numbers didn't match up. How about the last one? 2, and that doesn't even come close to matching the coefficients from the balance equation. Why? They're not elementary mechanistic steps. Okay? When we go through and look at rates of reactions, the coefficients do become the orders if it is an elementary mechanistic step. When you looked at Gen Chem, they weren't elementary mechanistic steps. So you had to go through and do fancy calculations and all sorts of other fun stuff. Why mention this? What was Chapter 7 all about?
Doing that fun stuff.
Elementary mechanistic steps, which means the rate expression comes directly out of your mechanism. It's awesome. That's what makes life easy for those. Okay? When we're looking at rate laws, okay, it is all about the slow step. Okay? And that's all this is getting at, trying to make you think about it in a different way, but you've already done this, so we won't worry about it. Your slow step always controls the rate of your reaction. How do you know it's the slow step? Your only step works, not necessarily your first step. What did you suggest? I think I heard it. Higher energy, be coming from your energy diagram. The difference in energy between your transition state and your reactant for that step. The largest that gap is, that's your slow step. That's the one that's going to dictate the rate for the whole reaction. Okay? So our experimental evidence. Okay? We'd have to go into the lab, we'd run a whole bunch of experiments. So if we looked at this reaction with those products, what mechanism occurred? Well, so it's rate times our rate constant times our ringy thing with chlorine on it times NaOH. It's scientific. What we want to know are the orders. What is M and what is N? How are we responsible for figuring that out? As a hint, you have to look at, oh, please reconnect. As a hint, you would have to look at all that fun stuff down there, a bunch of experiments. What happens if we compare trial 1 to trial 2? We look at our difference in our concentration. Our ringy chloride thing, did we change the substrate concentration? No. So that means if it was important, we wouldn't see a change in the rate, which means we see nothing. Well, that's not very helpful. No change means no change. Okay, thanks, Mr. Obvious. How about hydroxide?
Yes.
That changed by doing what? Doubling it. What happened to the rate? It doubled, which means the concentration of hydroxide was important to the rate. I could then go through a sequence of equations and solve for the order with respect to hydroxide, and I would find the order with respect to hydroxide was 1. I could go through and do the same idea for M to figure out what happened with that one, and I would determine, in this case, more than likely, but I didn't actually solve it, that M was 1. Which means this is what type of molecularity for a reaction? Bimolecular. Right, what type of reaction occurred? Substitution. So this would be an S and 2. There it is. So if you remember all that from 152, everybody liked that, right?
Yeah.
I shouldn't have put out my hand. Okay, so nobody liked that? Okay, I didn't like it either, so we won't be asked to be solving that. So instead what we'll do is look at our mechanisms. SN2. Okay, we need to break the carbon leaving group bond and simultaneously, yep, don't show that.
I know the answer now.
There's our leaving group, and simultaneously make the nucleophile bond. So how do I do that?
Draw arrows
Where?
from the
It's bond right next to him. I don't know.
Okay, the bond between the carbon and the leaving group, those electrons go where?
It's in the leaving group.
Okay.
And then nucleophile goes to that backside. No, carbon. The carbon's backside. It's going backdoor on it. Can you go to the right carbon? You know what I'm talking about. Thank you. Positively charged.
Okay. It would attack that position, kick out the leaving group, and we'd end up with our final product. Okay. Let's evaluate a little bit closer as what's happening on this.
Why did you draw it like that?
Why did I draw what like what?
Because it went down.
Why do I have the arrow being showed to go down there as opposed to up here?
Yeah.
Right. What did you say about the arrow?
Gotta go backdoor.
It,
What? That's what you said.
I did not say backdoor. It's a backside attack.
Backdoor, same thing.
You say it's worse.
It's the same thing.
Backside attack.
How much longer do I have?
Yeah. Backdoor.
5 weeks?
Backside.
What is the leaving group? What is it leaving with? Electrons. What is the nucleophile? Electrons. What happens when electrons get near electrons? They repel. Okay, so the nucleophile cannot attack from the same side of the bond where the leaving group is leaving because the electrons get too close to each other. So it has to go on the complete opposite side. Right? As far as our arrows shown here, is there really any difference between the two arrows for our nucleophile? Not really. Okay? Because what we're drawing here is a two-dimensional drawing. Okay? What we have to remember is that this is three-dimensional, and what I'm trying to do with the arrow is mimic as best as possible the actual directing of the attack. Okay? So if we went through to try and draw this a little bit larger, or not larger, but a little bit more detailed, we'd have something along those lines. Our nucleophile has to come in from the back side. It's going to come in right back here. Right? What happens to those hydrogens as the nucleophile comes in? I don't quite accept open up, but not too far off. What are they going to do with respect to the nucleophile? Move away from the nucleophile. Right? So they will actually kind of peel backwards. Right? So as this reaction is occurring, what I'll be seeing is that I actually transition through what kind of geometry? I'm drawing that horribly. I may just have to deal with my pretty picture in a second. What kind of geometry is happening about the carbon in the process of this reaction? I will sort of accept trigonal planar. If I look at the carbon substrate and the hydrogens, I'm going to be transitioning through a trigonal planar geometry. It would start to look an awful lot like an sp2 carbon. Okay? Not officially, because what else is happening? The leaving group is leaving, so it's still weakly coordinated, and the nucleophile is still coming in. It's still weakly coordinated. Right? So probably trigonal bipyramidal is a better pseudo comparison there. So what we're looking at is that transition. Right? Done with my hand. My wrist is the leaving group as best I can do it with my hand. My wrist is the leaving group. The nucleophile comes in from the backside. What are these? What are my fingers representing? I don't accept hydrogen. Don't accept hydrogens or carbons. Bonds. And what are bonds? Electrons. So as that comes in, what happens to the electrons? They need to repel away, and my hand would break all my fingers and go backwards.
Show us.
I'm not demonstrating.
We need a visual representation.
So we're getting the kind of reversion or inversion of those atoms. They flip or umbrella the other direction. Okay? What does that mean for the stereocenter if there was one? It very likely inverts because my nucleophile and the leaving group are very typically the highest priority atom, which means if I change the location of where the highest priority atom is, I get an inversion in the stereochemistry. So by evaluating the mechanism, I can predict something about my product structurally. Do I need to be worried about stereochemistry for this reaction shown?
No,
No. Why not?
because carbon was not chiral.
For me to evaluate chirality, I had better start with a chiral atom. There are two implied hydrogens. Can I tell a difference between hydrogens? Nope, which means I don't need to worry about chirality. Joey, you had a hand?
There's too many carbons in transition state.
No, but I can fix that. Don't worry about it. Not a big deal. And what we've now gone through and done is the substitution reaction. What I'm trying to show in the brackets there is a transition state. It must be shown in brackets. It must have double daggers. Why? I've exceeded the octet. That structure is not physically, possible. So what we're trying to show is what's happening to those atoms and how that changes the potential stereochemistry by looking at the transition state. Your mechanism cleanly is done at the top, and that's all we would need. Make sense? Okay. Big summary things. Rate. Okay. Since there is only one step, it's going to be dependent on the concentration of the reactants. Well, what reactants are there? The nucleophile and the substrate, okay, where the leaving group was attached. The word to associate with this is backside attack. You can put whatever you want. The biggest issue here is that we get electron-electron repulsion on the backside. So what do we want? The smallest backside possible. Okay? The minimal amount of electrons. Because our carbon will have to have 3 bonds on the backside, we won't be looking at the bonds, we'll be looking at the atoms that are connected via those bonds. And ideally, those atoms would be small, like hydrogen. Okay? The instant they become anything other than hydrogen, we start to slow down the reaction because the effective concentration of the substrate then changes. Because only one position is now, or that backside attack, can only happen when it limits, when we get some vibration that causes that larger group to move out of the way. That means your effective substrate concentration changes. What does it mean about the nucleophile? What kind of nucleophile do I want for this reaction? If I ask you to rank something, you're ranking it based off of electronegativity, lesser, weaker, stronger. What kind of nucleophile do I want here? Why do I want a strong one? Why is one step relevant? Why do I want a stronger nucleophile? Why is that important? What does the nucleophile need to do? It has to repel all the other electrons and move them away. What are we going to expect that nucleophile to supply? Electrons, and as strong an electron source as possible to help repel and launch those other things off. How can we get a strong one? That's where negative charge comes into play. Okay? How does that change our rate? Okay? Well, we think about our electrons as what's causing it. If it is negatively charged, those electrons are now more active. And what we're looking at is not a concentration per se, but the activity of the nucleophile, which is technically what it is. The more active our nucleophile, the higher the quote-unquote concentration. Okay? Yeah. What does SN1 look like? It's got an intermediate step because what do? The very first thing we do is heterolysis. We break the bond. The result of breaking the bond, I end up with a positive carbon and a negative iodide. Now what happens? I need my coordination step, which in this case is going to involve chloride. And now the chloride can come in and coordinate, and I end up with my product, which I don't know why I was writing a G. Okay. So if we take a look at our nice pretty mechanism, we've got it written out. Notice what else have I added here? There's also this weird extra acid-base step. Notice the note. Occasionally the third step is necessary. And the reaction that I showed before we drew, or that I drew out by hand, was it necessary? No. Why is this step necessary? Once the nucleophile attacks, the nucleophile became charged. Why would the nucleophile become positively charged? Iodide donated electrons too, and it did not become positively charged because it started neutral. So that's an interesting observation. In the SN1, our nucleophile starts neutral. In the SN2, it started charged. Why is that happening?
It's taking hydrogen from the nucleophile.
That's happening after the fact. What did we say we needed for our nucleophile in the SN2? It needed to be strong. For it to be strong, what charge did it need to be? Negative. And yet, in this case, according to this mechanism, what charge is my nucleophile? Neutral. The whole reason I needed a negative nucleophile was to speed the reaction. Why does it not speed the reaction for the SN1? There's more steps here, which means we have to look at our rate limiting step. Which of those steps is rate limiting? The slow step is our rate limiting, which is which one? It's going to be the heterolysis, the leaving group leaving. Why will that be the slowest step? Compare reactants to products in that first step. Forming charge. Is charge higher or lower in energy? Higher. So that's going up in energy. Is it easy to go up? No. All right, so that's not going to be easy. How about step 2? Okay, we're forming a bond, okay, but we still have charge. Why is step 2 not also high in energy? Step 1 was not just charge, it was octet. Step 2, we've satisfied the octet. We're still charged, but we're dropping in energy. Step 3, we've satisfied all our charges. We've gotten rid of our charges. Okay? So step 1 is the rate limiting step. Based off of our 152 knowledge, our rate is determined by our slow step. So rate equals the rate constant times the concentration of my reactants. What are the reactants in the slow step? Just the substrate. Do I care about the strength of the nucleophile? No. Okay, and in fact, the strength of the nucleophile does nothing for the SN1 reaction. So one of the big, quick, easy things we can look at. Do we have a strong nucleophile? Yes. What mechanism are we doing? SN2. No? SN1. Okay. So having in your mind, what are the things to be looking for, we can now help narrow those things down. The other thing we could evaluate, just like we did with the SN2, was that chirality issue. Okay. If I then made this a chiral atom, do I need to worry about it in the product? Okay. Do I get inversion? If I add that extra carbon. If that first one started as R, if it was SN2, it would become S. What does it become in the SN1? S. So in SN1 it does inversion. It can do both, I kind of accept, but not quite. We get two products. I would get both S and R. The question becomes why? Because SN2 you only got one. Why in the SN1 do you get two?
Because those electrons of the leaving group aren't there anymore. They've already left, so you don't have that repulsion.
Yes, sort of. What are we concerned about? We're concerned about the formation of the bond between the nucleophile and our substrate. In the SN2, where could it attack? Only the backside, because the leaving group was in the way. Where do we form the bond between the nucleophile and our substrate in the SN1? That's in our second step, and that's the nucleophile attacking what? A carbocation. What is the hybridization of a carbocation? sp2. Where is the positive charge of a carbocation found? That's the next question. Where is the carbocation found on an atom? In what orbital?
P.
It's in a p orbital, and a p orbital occupies both above and below the plane of an atom. We're still in that trigonal planar geometry. In the case of the SN2, we were transitioning in our trigonal planar. In the case of the SN1, we are formally in the trigonal planar geometry, which means the nucleophile can come in and either attack from the top of our carbocation or from the bottom. The result is two products. So because I have a carbocation, all the rest then follows. Kind of make sense? Okay. So we've got our rate, and that was pretty much it for our rate. There's our big summary. Two big products come out of that. Okay. What are our possible results? So here you go. Draw the products for both reactions. So we've got some skeletal structures up there. What is different about each of those notations? What's that? Yeah, we just look at those three structures. What's the difference between them? How we drew the benzene. One option, which I think I saw a couple people doing, was drawing the benzene and then showing a circle inside it. It's not that it's fully satisfied. Resonance. Those pi electrons can shift all the way around within that ring, so we can draw the hexagon with the circle in it. Okay. There's another notation drawn right above it, just the circle. Hey, it's saying we just got electrons moving around in a ring. What's the problem with that notation?
Looks like an oxygen.
That looks like an oxygen. So how can we do that and make sure it's not an oxygen? Just put a line through it. Now it's not oxygen. It represents phenyl. Or it represents the benzene ring. And the last one, we can just abbreviate the ring as pH. All of those are perfectly valid. I will say that the one with the slash through it is very, very rare. Okay? Most people don't abbreviate it that way, probably because that whole, it looks like oxygen thing. Okay. Where's our chemistry happen? Where's the leaving group? First carbon attached to our rings. Okay. In the case of the SN2, where's the iodine? Needs to be where the chlorine is, so our